Hello everyone, I'm Massimo Ruzzene from the Department of Mechanical Engineering at the University of Colorado Boulder, and I will present on our studies on the dynamics of two-dimensional lattices where no local feedback interactions are introduced and cause the system to be non-Hermitian. This work is co-authored by myself and Matteo Rosa, who is a graduate student in my group. Recently, there's been significant interest in mechanical systems that are non-Hermitian as a result of active interactions that are generally non-symmetric in space. And some implementations are presented here in the form of robotic metamaterials and other means using piezoelectric feedback actuation. And these configurations have shown new and interesting dynamic and wave propagation phenomena that includes non-reciprocal interactions or the onset of the skin effect, which is a localization of waves and modes at the edges of finite lattices. In this presentation, I will first introduce some examples of one-dimensional lattices to show the effects of non-local feedback interactions. These interactions are also non-symmetric, meaning that they only are applied either before or after a particular site. And we will describe how these interactions lead to non-reciprocal amplification and attenuation, frequency domain and frequency regions, and as indicated, the effects of modes localized at the boundary, which is a manifestation of the so-called skin effects. We will then talk about two-dimensional configurations, whereby these non-reciprocal interactions lead to directional amplification and attenuation of waves, and the onset of corner modes. In the case of one-dimensional lattices, we consider a lattice consisting of springs and masses, and in addition to the interactions due to nearest neighbor interactions due to the spring, we also consider an additional interaction that is the result of the deformation of a spring that is located a number of sites away from where the force is applied. And it's this interaction is applied in a non-symmetric way, which means that they're applied either to the left on one side of the site or to the right of the site, as shown here in this schematic. The resulting equation of motion has this added term where gamma c denotes the strength of these interactions, and these can be seen as feedback interactions where gamma c defines the gain of this feedback law that defines the strength of the interactions as said. If we look at a lattice of n masses, this can these equations of motion can be written in matrix form in an usual way, in a fairly usual way, where the stiffness terms that governs these interactions is non-symmetric, which is an indication of the Hermitian nature of the resulting underlying Hamiltonian of the system. From the governing equations, one can derive the dispersion relations of the system. And for the case, for example, where the feedback is local, as shown here, with a given gain, we obtain a dispersion relation that has both a real part and an imaginary part. The imaginary part is particularly interesting in this case because it's non-zero and it varies from a negative region for negative wave number to a positive region for positive wave number. If we look at the sign of the propagation operator in the exponential form, we observe that in the negative direction, this corresponds to gain or amplification as the wave propagates in space, whereas it corresponds to loss in the positive region of the propagating waves. So the domain gets separated into a region that undergoes gain and a direction where the waves are amplified versus a direction where they are attenuated. We can observe this by considering a finite lattice and applying a transient excitation to it over a broadband range of frequency. And if we look at the response of the lattice, we observe that the wave propagates only to the left, that is in the gain direction, in the direction of the gain, and it propagates backwards in this case, and it doesn't propagate forward, but where it's as a result of its loss in nature due to the feedback. An interesting observation to make is that if the feedback is non-local, as in this case, where it's applied one side away from where the force, the deformation of the spring, is determined, we observe that the spectrum in both the positive and negative wave number axis gets split in two regions, one corresponding to a gain and one corresponding to a loss region, which indicates that some frequencies will be amplified to the left, whereas some other frequencies all of them belonging to the green regions, will be amplified going to the right. So this can be simulated numerically by applying a force, again a broadband force at the middle of a finite lattice of 1500 masses, and we observe that the force applied in the center gets split into two main components, one in the higher frequency propagating to the right, whereas the lower frequency component, which corresponds to the green region, propagates to the left at the lower frequency. An interesting implication of the asymmetric feedback interaction is that the dispersion relations evolved in the complex plane. If we look at the evolution in terms of real and imaginary part as the wave number grows, we observe that there are closed loops that are formed that can be characterized by their winding number depending on whether they're clockwise or counterclockwise loops. In the case of a clockwise loop, we have a negative number, which is defined as a winding number, whereas in the case of a counterclockwise loop, we have a positive winding number. When we look at the modes of a finite system, the eigenstates of a finite system, depending on whether they fall within one of the two loops, we have modes that are either localized to the left, as in the case of mode 1 and 2, which are corresponding to a negative winding number, or to the right of the domain, as in the case of mode 3 and 4, which belong to a range that is characterized by a positive winding number. The behavior of these systems becomes even richer in the case of two-dimensional lattices, as shown here, and these lattices are characterized by potentially two different feedback gains that are occurring in the x and y direction, as shown here. In this case, each mass still has 1 degree of freedom, and they move perpendicularly to the plane of the screen, and they're connected to their nearest neighbors in addition to the connection associated with this feedback interaction that are highlighted by the red colors, as in these plots. For these cases, one can conveniently expand the governing equations to the two-dimensional domain and obtain in analytical form the dispersion relations, which are written here in terms of the gains in the x and y direction, and A defining the number of sites at which the feedback is applied away from where the interaction force is determined by the spring deformation. So the red denotes the additional term due to this feedback interaction laws that are added to the governing equations and to the dispersion relations. Like in the one-dimensional case, the dispersion relations are characterized by a frequency that has both a real part and an imaginary part. The real part is here represented in the wave number domain in the form of isofrequency contours, and the imaginary part shown below shows how there are regions that are positive and negative. If we look at a particular frequency of 0.7, for example, as identified by the black isofrequency contour, we show that the corresponding imaginary part varies from negative to positive according to the direction that corresponds to the associated wave number pairs. We can transform this representation in the form of a polar plot that shows the gain and the amplification and the loss or attenuation that occurs as a function of direction, here represented in blue and red respectively. If we animate this or simulate this on a finite domain, then we can see, for example, that this corresponds to the waves propagating in the direction of the gain,
with little to none propagation occurring in the directions other than those identified by the negative 45-degree angle.
This directional amplification and attenuation of waves can be tuned by changing the values of the control feedback strength along the y direction. For instance, as in this case, as we change gamma y for a fixed gamma x, we observe that the amplification of the wave occurs at different directions, as shown here, and as verified in the top row of the slide, and as verified numerically by the results shown in the bottom row of the slide.
The case of non-local control is even richer and more interesting, where we have these isofrequency contours and the imaginary part of the dispersion relations that are here tracked as a function of three values of frequencies, and the imaginary parts are transformed in the form of these polar plots for the three frequencies under consideration, which show that the gain and loss occur both in different directions and at different angular values, as shown here. And this has the effect of decoupling a broadband impulse applied in the middle of a finite lattice, for example, which causes the various frequency component to travel in different direction and at different angles, as shown in this case from the snapshot of a finite lattice time domain simulation, showing again that the low frequency component propagates to the negative 45-degree angle, whereas two higher frequency component propagate in the positive half space, let's say, at different frequencies corresponding different directions.
These properties can be exploited in the case of a finite strip which is bounded along the x direction but is infinite along the y direction, as shown here. The dispersion analysis of the strip relies on the governing equation and block analysis conducted or imposed along the infinite y direction. The dispersion analysis conducted on a finite strip leads to a series of branches, which are here color-coded based on the corresponding winding numbers, with blue being associated with a negative winding number. And these branches are also characterized by an imaginary part that is positive and negative, indicating amplification and attenuation, which is directional in nature. We can observe that, for example, for excitation at the corresponding frequency of about 0.4 for an input corresponds to edge localized modes along the x direction, and then it corresponds to gain in the negative y direction as opposed to loss in the positive y direction. When looking at finite lattices, complete finite lattices in the x and y direction, the directionality of the gain and loss behavior manifests itself or leads to modes that are localized at the edges that correspond to the directions of where the gain occurs. As in this case at 0.6, we have that the modes are localized at the bottom lower edge, whereas for the frequency of 2.5 here, the modes are localized at the top right edge that corresponds to the direction of gain, highlighted by the directionality plots and by the blue curves in the directionality plots specifically. In conclusion, we have investigated feedback interactions as a strategy to introduce non-Hermitian phenomena in lattices, and we have observed unconventional wave phenomena such as non-reciprocal amplification and localization of waves and of eigenstates that occurs at edges and corners of finite lattices. This opens possible future work directions that include the experimental realization of these concepts and the exploration of different geometries and the modulation of control parameters across the lattice. In closing, I want to acknowledge the support from the National Science Foundation and from the Army Research Office, and I want to acknowledge the work of Massimo Ruzzene, who's the lead contributor in this work. And I want to thank all of you for the attention and for the interest in this work. Thank you very much, and I'm hoping to see you all very soon.